It's getting there. It's a slow business, but I'm getting there. And I'm interested in games operating in higher dimensional space. I'll just talk very quickly, obviously, what is 4D, how we can relate to 4D. There's a little demonstration of a puzzle game which involves 4D geometry. Then look at the question, is it all too difficult? The answer will be now, I can tell you, no it's not, but it is hard to relate to 4D. And then a little bit at the end about how 4D could possibly be used in real life games. Right, very quickly, I'm sure you're familiar with all this, but I'll go over it in case. How many dimensions are there? We live in a 3D world. Well, we're familiar with 2D Cartesian geometry. There's 2D, which I'm sure you're familiar with from school. We extend that to 3D, no problems at all. Can we extend it to 4D? No, we can't. We just run out of space. It's interesting that the mathematics on the right has no problem at all. You can extend that as much as you want. But the physical world isn't up to scratch. We run out of dimension down to 3. We can arrive at the same conclusion in a different way. We start up with a 0-dimensional object. We can extend that in space, and we end up with a 1-dimensional object. Okay, now we'll take that process up to the next level. We start with a 1-dimensional object, move it through space, we end up with a 2-dimensional object. Good, let's continue the process. We start with a 2-dimensional object, extend it through space, get a 3-dimensional object. Good, let's continue. We start with a 3-dimensional object, we extend it, whoops, no problem. So you get the same thing here where there's a logical argument that you can follow, a mathematical argument you can follow, but the physical space just runs out of dimensions. But we can obviously represent higher dimensional objects using various tricks, such as perspective and projection, things of that kind. In other words, the sort of things that you are familiar with in normal computer games. In the case of the hypercube there, we're actually losing 2 dimensions because we're representing it in a flat surface here. So there's all kinds of tricks going on there to try and cram 4 dimensions into 2, which is a lot harder than 3 into 2. And this is just to reinforce the idea that in mathematics there's really no problem. And this is important because all the geometry for rendering, like you've probably come across your projection matrices in OpenGL. Well, actually it's really easy to extend that to a projection from 4D into 3D. It's really the same structure. Okay, this is something I'll just skip over. We can conceive it mathematically, can we actually see it? If you're interested in pursuing this, you can look at Charles Hinton. He lived about 100 years ago. He claimed that he could actually see 4-dimensional space. He didn't say, I can conceive it. He didn't say, I know all the maths. He said, I can really see 4-dimensional space. Poincaré, eminent mathematician, who equally ought to know what he's talking about, said, no, absolutely impossible, cannot see 4-dimensional space. So that's just an interesting side. Okay, how can we relate to 4-dimensional objects? I'm going to concentrate on 2 things here, projection and intersection. Projection has been around for a long time. Anytime you look at a flat screen rendering of let's say a painting, you're looking at projection. It's been around for a long time. It's what's used in computer games, rendering 3D scenes. Projection gives us perspective. That's the sort of thing you see in a computer science book about graphics. Taking going from 3D onto a 2D screen. Right, now here is the projection of a 2D object into a 1D space. It reduces to a line. There is the intersection of a 2D object with a 1D space, which is a rather different line depending on the position of the square. And now if we include them both, you get slightly more information about how the 2D object relates to the 1D space. So that's the technique that I'm going to show you in a second with my little demonstration. It involves both projection and intersection. Because what we're doing is we're projecting a hypercube into 3D space, and you saw a still rendering of that earlier, where you have a sort of outline, it's a wireframe outline. But I'm also taking an intersection of a hypercube with 3D space, which is a solid object. But you actually get more information about the orientation, for the point of view of the puzzle, if you superimpose the intersection on the projection. Okay, and just to make that point, here is projection from 3D to 2D. There's an intersection which by itself looks a bit silly, but if you combine the two, you imagine the corner of that cube poking forward through the screen. It gives you a little bit more information about how the cube is oriented. Okay, I'll now try and give you a demonstration. I'll just go through and describe what's happening here. What you have is on the left, you've got a, well, let's just, right, that's the projection of a 4D object of a hypercube onto 3D, and you're probably familiar with that kind of rendering. It's similar to what you saw before. Now what we have on the right is a hypercube in a random orientation. And every time the game starts, it's at a different random orientation. And on the left it's in a self-playing mode, of course, at the moment. On the left is a hypercube it starts in a standard orientation, and the purpose is for you to rotate it until it coincides with the orientation of the other one. And in order to do that, you have to have some concept of rotating in a higher dimensional space. In fact, the rotation in 4D space involves 6 degrees of freedom, as opposed to 3 degrees of freedom, which is when you're using a joystick in 3D space. So, okay, that's the projection. Let's look at the, if I can bring it up. That's the intersection, which is like a, it's an object that changes its shape, basically. Now, what about the colours? If you imagine a cube which has 6 faces, and each face has a different colour, if you imagine that intersecting with a 2D space, let's say a tabletop, then the intersection points would be lines, and each of the lines would have a different colour depending on the colour of the face that you're intersecting. Well, here we've got an analogous situation. A hypercube is actually a 4D object surrounded by 8 cubes, and each of these cubes has a different colour. And as the object rotates through 4D space, different cubes intersect with our 3D space. So that's where the different colours come from. So you can use the colours as a sort of guide as to which cube is intersecting. If I bring them both together, that's the intersection and the projection. Okay, now at this point, this is where I get very nervous, because I'm now going to actually try and solve the problem. So I'll just and I may not do it. When I presented this last time, I sort of panicked after about 2 minutes, and I abandoned it. But basically, I'll just show you what the little puzzle is. I've got to try and rotate that cube on the left until it coincides with the cube on the right. And what I'm going to do is I'm just going to cheat, alter it so that it looks reasonably easy. So that looks reasonably easy. Okay. I could kind of do a running commentary. I think it would actually be too hard. Okay, now what I'm doing obviously at the moment is lining it up in a 3-dimensional sense.